So in this section of the video, I'm going to be showing you what it looks like to do neutral ground bonds, and I'm doing that with the panel cover removed. Recognize that this is essentially an unsafe working condition in that my utility side is energized and my house is energized. So that means any of the shiny bits can be energized at any point in time, so we don't touch those. In addition, I do have insulation around my incoming lugs coming from the utility, the line side of my breaker, but just because I have them insulated off and there's nothing live that you could possibly touch, you still have an arc fault possibility here that could obviously hurt you. So I don't recommend that you work in your panel hot ever. I don't recommend that you remove your panel cover when it is energized ever. If you would like to remove your panel cover and inspect and play with your grounds and fix things that are wrong, I strongly recommend you have your utility remove the meter from the socket while you do your work, so that way your panel is truly energized. And then when you're done, you can call them back, have them check your work, have it inspected. This work was inspected by the city, and all work electrically should be inspected by your municipality. Let's talk a little bit about this. What is a neutral ground bond inside your panel? Now, this is a 200 amp square D home line that I installed when I moved into this house. It originally had a Federal Pacific 200 amp panel that was dangerous and old. So this green screw that you see right there, that is your neutral ground bond point. The neutral bar is in the center. You can see the conductor with white tape on it. That bonds directly to the chassis, and then I also have a ground lug on here. So this is my neutral ground bond point. I only have one of them in the entire system. I have a sub panel in the garage, in which case the ground and the neutral are isolated because you could only have one. This panel, the grounding conductors that you see, which are the bare copper, they go to natural gas piping, water piping, natural gas and water. And then another one hits that Schedule 80 PVC, runs down the wall, goes outside to my ground bar. That's all low voltage for like transformers and intercom and X10. Now for the generator connection, that's my generator breaker. You can see it's currently off. It has to be located in the top right in order for the panel mechanical interlock to work. And if we take a look at that, you'll see that this is how that system works. It basically bolts to your panel. You have to drill it out. The generator connection was made using ENT, electrical non-metallic tubing, also called Smurf tube. I did that for 3 reasons. I wanted to come into the bottom of my panel because the top's getting full, and I want to also bring in some EV car chargers in the future. I had a specific length of wire that I didn't want to go and buy another spool because wire costs are extremely high right now. And I wanted it to be non-metallic because I'm lifting the ground wire here. All right, looking closely at this junction box, this is coming from my panel, and that bare ground is coming from the generator receptacle. So you can see that this is insulated and lifted, and this box is actually bonded from the generator side. These conductors are pre-twisted fairly tight. The caps aren't actually holding them together or holding the wires together, they're just insulating the end of it. This is important that you properly, if you're going to make a splice in anything high amperage, you pre-twist. It's my strong recommendation. The wire nuts just really hold the wires together like this. They don't actually twist them together. So this is lifted, and we're going to look at some diagrams, and I'm going to explain why I believe this is a better scenario than having 2 neutral ground bonds when you're going to backfeed your panel.
In these images, we're going to see yellow being represented as the source current, blue as the neutral return current under normal operating conditions, and red as the abnormal current. In this case, when we have 2 neutral ground bonds, current splits at the neutral bar and goes through the second source, which in this case is the generator, meaning the neutral and the ground have current on them, which is half of the normal neutral current when the generator is not on anytime it is connected. This is problematic and something we're going to pay attention to in other diagrams. Now, when we have a fault with the utility as a source, we're interested in how that fault current makes it back to the source. And in the case of dual neutral ground bonds, we see a second path, just as we did with normal neutral current, in which abnormal fault current comes back around through the generator on the ground and on the neutral to get back to the source, which is again problematic. So the previous diagram showed what happens when we have a utility source. Now we're looking at a generator as a source, which is typically what you're going to run into whenever you're connecting your generator to your panel through a backfed circuit breaker. And of course, as expected, when we have two neutral ground bonds in the system, we're going to have parallel paths for a neutral current. This is a problem. And this, unfortunately, is what I think most panel backfed generators are suffering from. We're going to take a look at what happens when there's a fault condition. And then after that, we're going to take a look at some solutions that I think can maybe solve this problem for low cost for most people. The receptacle enclosure itself is a possibility for electrocution, which means it has to be bonded. How do we bond it? And how do we bond it in each type of system? If we have parallel paths, of course, we're going to have parallel paths for fault current, and it's going to travel back into the panel and then come back around the neutral, besides the parallel path being the ground. You can see this is a problem. I don't even know why I have to keep explaining this, but we're going to talk about one more scenario that is not any good. For each of the possibilities, we're going to analyze both normal neutral current and abnormal fault current, because that is the process necessary to determine that we have a safe operating system. Here we see, yet again, we have parallel paths when we have two neutral ground bonds. I'm trying to drive in with each of these images. This is a bad idea. This is why the National Electric Code says don't do it, and I concur. Don't do that. Let's look at some solutions. And now, the moment you've all been waiting for, a solution. So if we take a look at this generator receptacle, we can see that I've not connected the grounds together. I've lifted the ground to match the photo that I showed you earlier. And by doing this, we break that circular connection that I was getting tired of talking about. So what does this actually mean for you installing it? Well, it simply means that the generator cord that you're going to buy to connect your generator to the receptacle, kind of like I show here, that cord is going to be 4 wires, so you have to maintain all 4 wires from that point to the receptacle. But you simply bond the enclosure of the receptacle and then lift the ground coming from the panel. Now, you could omit it entirely, but I left it in there just in case I ever decided to do something different with my generator in the future. So let's go ahead and take a look at why I think this works and the proof behind it. The first scenario is what happens when the generator is a source. Well, just as you saw with the utility as a source, we have broken the parallel paths. That means normal neutral current only takes the normal path through the neutral conductor. It does not have a parallel path through the neutral ground bond in the panel to thus generate current on the ground. You can rewind to take a look at that. So now that I have resolved that problem, let's take a look at what happens if there's a fault, because we have a few concerns that we need to make sure that we've resolved before we essentially assume this is an acceptable solution. The first, of course, is what happens if the generator is connected and we have a utility source and there's a fault on one of the branch circuits. Do I have a parallel path back to my genset? The answer is no, because I broke that ground connection. I no longer have a parallel path. Therefore, this essentially resolves that primary concern. Now let's look at what happens when the generator is a source. As expected, when the generator is a source, we've also resolved the parallel paths by breaking the ground connection at the generator receptacle. Therefore, this is essentially looking like it's a pretty good solution. Now, we have to take one more item into consideration, and that is, what happens if we accidentally energize the external metal case on the generator receptacle itself? Well, what do you know? I have a diagram for that too. As expected, if we bond the generator receptacle enclosure to the ground coming from the generator, we have a pretty clear path back for fault current. Now you might ask, well, what happens if the utility is the source and we don't have a bond from the utility ground to the receptacle enclosure? Well, the answer is nothing, because we have a mechanical interlock that prevents paralleling those two sources. Therefore, the generator conductors themselves, the red and black cables that you see in that generator receptacle, cannot be energized by the utility. Therefore, we don't actually have an opportunity for a fault. So there's not necessarily a problem there. And if we had an inadvertent bond from the neutral to the ground, nothing would trip. We wouldn't know about it. We had neutral currents that were circulating around, which would be problematic, and we should probably insulate any neutral conductors when we're inside this enclosure to ensure that that does not happen, just the same as we have to essentially insulate any ground conductors inside this enclosure to ensure that this does not happen, which you saw I did in the previous photos. This is essentially a proof of concept. I think that I feel pretty comfortable saying that this is a way that you can isolate your generator from utility when you backfeed your panel and have a neutral ground bond in both locations. Lifting the ground and not the neutral is what I feel an adequate solution. Now let's take a look at one other scenario and decide whether or not we like it. Now, if you have a permanently installed generator, this is an appropriate solution. Lift the neutral ground bond in the generator and maintain all 4 wires, phases, neutral, and ground, back to your panel, and only have one neutral ground bond in your main panel. Again, this is great for permanently installed generators, but I wouldn't do this for anything that's a portable generator. When we break that neutral ground bond in the generator, we only have one in the system. As you can see with the utility, we're completely fine. We have a normal path all the way back, and we lost our concern that we've been kind of beating to death in all these previous videos. So this works for the utility source. Now we're going to take a look and see that it also works for the generator source, and then go through our typical fault current images. Just as with the utility, of course, if we have the generator as a source and we've lifted our ground and neutral bond in the generator, we have eliminated a parallel source. So neutral current will simply take the normal path back. Nothing abnormal here. Now let's take a look what happens when we have a fault. As you should have expected, when we don't have parallel paths and we have a fault current with utility as a source, we don't have parallel paths for fault current. It simply comes back on the ground, goes to the neutral ground bond of the panel, and heads back to the source. So then that way the source can see it and our breaker can trip. This is all fine and good. Now let's take a look what happens when the generator is a source. Now if we have a fault on one of our branch circuits with our generator as a source and our generator set up as shown, we have a path back to our genset. That path back just happens to be through the neutral ground bond within the panel. Now, what you might ask, is that a problem because my fault current's taking a different path? Well, all I'm trying to do is get it back to the neutral anyway, because that's the path to my source. So whether that neutral ground bond occurs in the panel once or it occurs in my generator, essentially the result is exactly the same. And commercially, when we have non-separately derived systems like you see here, and we have one neutral ground bond, this is essentially how fault current makes it back. So commercially, it's perfectly acceptable, which means it's also acceptable for your home. If we have a fault within the generator receptacle enclosure, that metallized surface needs to have a path back to our source. And in the case of a lifted neutral ground bond of the generator, it's going to take a path through the single neutral ground bond in the system. And this is okay. That path gets us back to our source. It may seem weird, and I did draw it in red. I did that just to identify that it's an alternate path that we would normally expect, and it's different from the previous diagrams, but it's still okay. We have that path back. So hopefully from all of this, you learned to basically study the paths that fault current and normal neutral current can take in a system. This is why only one neutral ground bond is required in a system, and why when we connect generators, we have to pay close attention to that. It can cause damage to your generator, and it can cause damage to sensitive electronics in your home. Now you'll notice the ground rod that's to the far right is not connected in this case, and I'm going to talk about that and kind of bounce back and forth because I did show another image that had it. Now, real quick, you may have noticed that the connection between a generator ground rod and the generator chassis only appeared in one of the scenarios, and that is where we had lifted the bond in the receptacle. You may ask why that is. Well, the generator manufacturers require that you have a separate ground rod specifically to bond the chassis of the generator to earth, to have the same voltage reference and to help allow any of the overcurrent protection work in the event of a fault to ground. So do you need to do that when you have your generator ground bonded to your home panel ground? Well, no, because you have a ground rod there. You have a low impedance path back to that. But if you're going to lift that, suddenly you have introduced the need for a dedicated ground rod. Now, I didn't talk about that in that video, but I did want to mention ground rods essentially give your panel a reference to earth, and that reference is shared with the utility. This is why it's important to maintain that grounding of your electrical system to earth, and why if you have a break in that, you can tend to have problems with voltage instability. So if we take the cover off of our generator, we can see the neutral ground bond point within it. This is essentially how you confirm whether or not your generator is bonded or not. And it's likely going to be from the factory because it wants to operate in standalone mode, not just when connected to a building. And of course, if you have a neutral switching transfer switch, then you would leave this connected. You could refer to our previous discussions about when this is lifted, but you can see for my purpose, I'm leaving this connected and lifting the ground at the receptacle. So after all of this, what generator did I buy? Well, I like Generac from a commercial standpoint, and they make a decent residential product. So the 8500 EFI, or the XT 8500 EFI, is fuel injected, which means I don't have to deal with carburetors and carburetor fuel. It has CO Sense, so it's not going to kill me. It's got an electric start, and most importantly, it's got low THD, 5% or less on the output, which is actually hard to find in larger gen sets like this. A 30 amp 240 volt twist lock receptacle allows me to backfeed my entire home. Now, when I bought it, it was like a factory resale, so it had 4 hours of use on it. I filled it up full of oil, did a test of the battery, kind of tested the rest of the system out, and here's a demo of what it sounds like.
All right. If you were savvy, you might have noticed that I kept talking about a generator receptacle, but I didn't talk specifically about the junction box on the inside of the house that you saw all the time. Well, what I did is used a sleeve of threaded rigid metallic conduit to connect the exterior generator receptacle to the interior junction box. And I had an interior junction box because of the placement of that receptacle was very precise on the outside aesthetically, and where it was in relationship to my AC connection. And that happened to line right between a pair of Schedule 80 conduits that I had already used, so I needed to basically pass through, and then I needed to change orientation. I didn't want to do a 90 that stuck out. I wanted to stay a little bit tighter to the wall. And as I also mentioned, wire costs right now are really high. I had enough 10-3 plus ground laying around to utilize for this project, but ideally I would reroute that entirely and get rid of the ENT. Smurf tube, it technically works, it's just hideous. So I can get Raceway to pop up to the rafters and then reroute around. But again, as I mentioned, the top of my panel is also getting full, coming into the bottom. In this case, was pretty handy. So we'll see what I want to do there, but I did want to touch on the difference between the interior junction box and the exterior receptacle, both of which are bonded from the generator side. Anything metallic, metal, can conduct, you have to bond that. I also want to talk about a couple other things you might have noticed. In my panel, I have a plug-on neutral. I talked about the neutral ground bond in the very beginning. I didn't mention that I have separate ground lugs, grounding bars inside the panel on the chassis. So all my circuits that wire in, my neutrals go to the plug-on neutral bar. My grounds go to the ground bars. I didn't utilize one common one like you see in some panels, just as a habit to try to maintain. And that also might help me later on in the future when I put in a whole home transfer switch in place of those funky LBs that I was talking about. Third thing I'll mention is you might have seen a lot of 2-pole breakers in my panel and wondered what that was about. I have multi-wire circuits in my home. That's where 12-3 with red, black, white, and a ground was used to power 2 circuits in the house. Pretty common way to save a little bit of money back in the day. But National Electric Code requires that you have handle ties between those two circuits or use a 2-pole breaker. For the same reasons I showed you that there's neutral current, if you shut off only one of the 2 circuits, you can still have current on that neutral. You go to work in the panel, creates an unsafe condition. So if you see a lot of 12-3 and a lot of red and black wires that serve outlets, lights, receptacles, etc. in your home, those need to be on 2-pole breakers for the same reasons that we've discussed. Hope that clears up a few things you might have noticed. Well, this video has been a lot of fun for me, and I appreciate everyone's patience. This was the predominant topic in all the comments. What do we do? How do we bond this? How do I do a backfed panel? generator configuration. What does that look like, and how do I do it safely? What do I do for bonding? There seems to be a giant miss out there in this topic. I watch their videos, they talk about it as an idea, but nobody's making a recommendation. And that I understand. As a electrical engineer and a licensed professional, I have to be very careful about taking on any liability. And if I'm going to provide recommendations to the internet, essentially there's some liability that can be taken. So I have to say, I'm not providing recommendations for you personally. I'm simply saying, I went through the study of what I would do in my own home and maybe what I would do for somebody else's. And if I was to design something and sign and seal it, then I would do this sort of thing. But only under my supervision, essentially my recommendations could be safely taken. I put the disclaimer at the beginning that everything should be inspected. Yes, you should not open your panel while it's energized. That is true. Utility company is happy to come out in their convenience, remove the meter from the socket, which de-energizes the inside of your panel, lets you take the cover off safely, inspect everything, safe off stuff, and go through the process of adding a generator breaker and adding the interlocks and making sure your grounding is good, and then get that inspected. If you're a licensed electrician, essentially you're just looking at this to figure out what is the thought process that I went through to come up with any determinations for what I'm doing. And if you're a homeowner, well, then you should get this either professionally installed or certainly inspected. Assume that there's things you don't know and that an inspector does know and pays close attention to. And the method of grounding is one of them. And the method of bonding internal systems is another. So you got to get that stuff right. Now, we are really interested in this topic because it's what most of us want to do. We want the flexibility of simply having the entire panel available to us. Maybe not all at once, because our generator's not big enough for that, but at least one at a time, 2, 3 at a time. So the method that I use to connect my generator to my whole home panel, utilities out or not, if I'm going to do a test, I open the utility main breaker. So I've disconnected my panel from the utility. Then I open every other breaker in the panel. Everything is essentially off at this point. Wheel my generator around, connect it up to the house, start it. Pull cord or push a button in my case. Let it warm up 3-4 minutes, and now it's ready to accept load. Now, it's all about work. Like if you're driving and you go up a hill, your car slows down, you have to give it gas to change the air-fuel ratio to make that engine produce more power. The generator's no different. It takes more work to produce electricity, to physically spin the generator portions. So the engine has to react to that, which is why we don't just turn on the whole panel at once or just flip the main breakers only. We actually individually turn on every single circuit. And now you might already pre-label the ones that you want, like your refrigerators, your freezers, maybe your furnace. But maybe you want to do a garage door opener, or you want to run a dishwasher in an extended outage. You can when you're backfeeding your panel. It's actually the reason we do it in the first place. I didn't go into a lot of detail on transfer switches, and that was intentional. You saw that weird double LB configuration and probably thought I was being weird. When I replaced my panel, of course, that's where the old panel was, and the meter socket was recessed in the exterior of my wall, so that wasn't going to change. And I had to get from there to my other panel location, which was taller, and I wanted to make room for a whole home transfer switch in the future. Ideally, that's where I'll end up, was a nice big whole home generator that's going to sit outside permanently, natural gas fed, and then that will run through a whole home transfer switch and do it all automatically. That's a long-term goal. But in the interim, $1,000 portable 8,500 watt fuel injected generator made a lot of sense to me. So I wanted to be able to have that for now, and then maybe in the future I do the more elaborate system. But we're always thinking ahead when we're installing things so we don't screw future self. Now I hope this has been helpful, also in a process of how you solve problems. I had the question, and I didn't actually know the answer before I started all of this. It took time to develop diagrams and study them, looking at National Electric Code Articles 250, for which is grounding and bonding, and of course, 240 and 220, 110. And then also I had to look at IEEE Green Book, which is essentially this nauseating level of detail for grounding and bonding. We want to make sure that these are safe and these recommendations are safe. So I'll try to put a focus on that. I expect a ton of questions. Anything that comes up, if you have a question, please ask. I'm happy to answer it. And if there's enough of the same question, then that means that we have to do another video to break it down and explain it. So thank you for sticking with me. Thank you for watching these things. They are a lot of fun, and thank you for your patience as I try to work them all in. Have a blessed day.